Up to this point, we've worked with convolutional neural networks, more specifically 2D convolutional neural networks, which have to do with 2D inputs. Now, we shall see how with 1D convolutions, that's the conv 1D, we are going to be able to work with 1D inputs. Recall that is the cross correlation operation and not the convolution operation. The formula for the 1D cross correlation operation is a simplified version of the 2D convolution operation or the 2D cross correlation operation. Here we have that an input, for example, like this one, where we have 6 values or 6 different points in this input. When cross correlated with a filter f, like this one, for example, with 2 points, to get each and every value in the output, we simply have the sum for all h of the input I of I plus h, where I is the input index, times f of h, where f is a filter. Now, this formula we had seen already still maintains, where to obtain the dimensions of the output, we simply have the dimension of the input minus the filter size plus 2 times the pattern divided by the strides plus 1. So in the case where we have the input like this, which is equal to 6, we have 6 minus the filter size 2, which is 4. 4 plus 2 times the pattern is 0, so we have 4 divided by the stride 1, so we have 4 divided by 1, which is 4, plus 1, which is 5. So the output, or the dimension of the output, is going to be equal to 5. So that's why we have 5 different positions right here. And then to obtain each value, we'll simply multiply this with the input term by term. So we just take this filter and then feed it with the input. So yeah, right here we have minus 10 times 3 plus 0 times 2. So it's practically the implementation of this formula, where if we want to calculate I0, for example, that's the output 0, we have to sum for all h, IH, because I is 0, so we're looking for IH, f of h. Now when h equals 0, we have I0, f of 0. Now this is I0 and this is f of 0. And then we move to the next. When h equals 1, we have I1, f of 1. So this is f of 1 and this is I1. And that's how we multiply I0, f0 and then add it with I1, f1. So that's how we get the result here. Now we've added these 3 others to show that in a case where we have many of these inputs stacked, we can actually, for each of these inputs, have some kernels, such that to obtain the final result, we multiply this, we have minus 30 plus 0, that's minus 30, and then we add it up with these other results as we saw with the 2D convolution. So right here we have minus 30 plus, this is 0, this is also 0, because here right here we have zeros. This is 9, 3 times 3 is 9, plus 3 times minus 2, which is equals minus 6, and then 9 plus minus 6 is 3, minus 30 we had right from here, plus 0 plus 3 will give us minus 27. Now obviously there should be a bias, but for now we're supposing the bias equals 0, so that's why we just concentrating on the values we got from the weights, because now these are our weights. So that's how we do to obtain this first value, and then we move to the next. So our stride is 1, so we just simply slide over to the next 2 values with our kernel. We do the same and we obtain a value of 25. Slide to the next, we obtain a value of -10, to the next, obtain a value of 110, and then finally obtain a value of 13. So that's how we obtain this. And recall that we have seen that the output dimension was equals 5. So we have those 5 different positions. So this shows us clearly how working with 1D convolutions looks like. Now let's come back to the context of sequence models. Recall that with sequence models we have different time steps. So we could have the 0 time step, which is this, the first time step this, the second, which is this, the third this, the fourth this, and the fifth this. Or you could start from the first, second, third up to the seed. So those are different time steps. And generally for each time step, we have a certain vocabulary size. So that's generally how our data looks like. Now, here we've chosen a sequence length of 6 and we have a vocab size of 4. That's why we have 4 of this stacked. So this is the, say, first time step. Now in this first time step, what happens is we pass this through a 1D convolution. Or to be more clear, we just pass all this into a 1D convolution, such that, as we saw previously, for this one we're going to obtain this 5-dimension output. But to obtain this value, what we've done is we've combined this, and this. So we've gone through the data vocabulary wise. So we've gone through the different points in the vocabulary, while also going through the whole sequence. That's via each time step. And with this, clearly we see how we are able to lead from this input to this one. Now recall that with RNNs, that's the simple RNN, the LSTM, the GRUs, generally when they get this kind of input, not forgetting that we also have the batch size. That's the shape of the input is batch size, sequence length, vocabulary size. For now we're leaving out the batch size. So when we get this kind of input, the output is of form, sequence length, of shape, sequence length, and a certain number of units. So if our vocab size is say 4, we can end up with just 2 units. So we can end up with this and this. But in this particular example, we just have 1 of this. So our output unit is equals 1 in this case. So see exactly how this works out, very similar to the LSTMs. So with this, we see how we slide through this and finally obtain all our values. Now in order to vary the dimension of this output, we could have the kernel size being different. So in this case where our kernel size equals 2, we could modify this. If for example our kernel size equals, for example, 4, then we should have a different sequence length for the output. And then the number of output units is defined by the number of kernels we work with. Now let's see how to work with a 1D convolution practically. As usual, TensorFlow already comes with this module, so we shall just see how to use this. Now we have the inputs, we have the embedding dim. Notice that we've modified this now to take into consideration the sequence length. We want to mimic the exact example we had on the slides where we had a sequence length of 6. And we also want the embeddings to give us an output of 4, so that we have 4 kind of our vocabulary size getting to the convolutional on the 1D convolution as 4. Now this is different from the vocabulary size here, because in the slides we're supposing that there is no embedding. So basically what we're trying to do here is just see exactly or have the same results we had in the slides. So with that, we now define the 1D convolution, the number of filters or the number of kernels, the kernel size, which is 2 as we saw on the slides, max pooling again. So it's very similar to the max pooling we had seen before. We just go through all the sequence and then select the maximum from a given range of points in the sequence. In this case, the range is 2. That is the number of points we're working with is 2. So for every 2 points, we select the maximum and we discard those 2 points. So actually from 2 points, we output 1. So that's why generally we have our dimensions divided by 2 after max pooling. From here, we have the global max pooling, which is going to be used for us to put our information in such a way that the dense layer can take it and then output in such a way we could train it very easily, since we're solving a classification problem. So we run this and we see this clearly come out exactly as expected. Now we have the sequence length, which leads from 6 to 5 as we saw in the slides. The number of or the vocab size goes from 4 to 1. I repeat, the vocab size we have here is not the same as this vocab size, because in the slides we didn't consider that there's an embedding before the conv 1D. So That's why we're considering this 4 as the vocab size. So the vocab size goes from 4 to 1. After the max pooling, we go from 5 to 2. And then do the global max pooling, all this is combined into just one value, which is now then passed to a dense layer, and there we go. So again, here we compile our model and then we train the model. We're actually having these errors because this is not exactly the inputs we are supposed to put in. So let's take this off. From here we have this, the embedding dim. Okay, so that's it. So we could run this again, compile the model, and then train it. After training for over 50 epochs, we have the following results. Now we'll notice that these results are not as performant as with the LSTM and GRU models, or even with the simple RNN models. So it shows us that the 1D convolution may not have been the best suited for this, or even that we need to actually modify this initial model. So instead of working with just this one kernel, we could increase the number of kernels. So if we have, say, 100 kernels, and then after this max pooling we include another of this, so we could do this, we could have something like this. So if we run this now, let's take this to be, say, 64 and put this to 64. Let's have this. Then right here we reduce the number of epochs. Take this, run it again. After training for over 15 epochs, that's after modifying our conv1D model, we see that now we have better results which are comparable to what we had with the LSTM and with the GRU. So it just suffices to remodel this better as we just did. Let's now run this and see what happens with the loss. We see that the loss actually now drops to acceptable values, and then the accuracy goes up to close to 80%. That's very close to what we have with the LSTMs and with the GRU. So this shows us how good the 1D convolutions are when it comes to sequence modeling.